Yes, hello students. In this lecture, I will explain the second method of speed control, that is frequency control. You recall that the synchronous speed of the motor is given by 4 pi f upon p radians per second, that is equal to 120 f upon p rpm. And the motor speed is given by omega ms 1 minus s. So if we change the frequency, synchronous speed will change and the motor speed will also change. So by changing frequency, you can change the speed of the motor. But there is one more aspect that you have to see. What is the effect of change in frequency on the flux of the motor? Because the torque produced by the motor will depend on flux produced by the motor. So let us recall the equation of induced EMF in the stator winding per phase. It is given by E equal to 4.44, the winding factor, into turn per phase, into frequency and the flux per pole. So let me give this a name. It's 4.44 kW TPH. It is a constant. Let me call it kW dash into F into phi. Now from here you can write phi is equal to E upon kW dash into F. And as you know that the stator induced EMF will be close to the per phase input voltage. It will be V minus some drop in the stator winding. So if we ignore that voltage drop, then you can write that this is equal to V upon kW dash F approximately. So this is equal to V upon F upon kW dash. So this means that when we reduce the frequency to reduce the speed of the motor, the flux of the motor will increase. At rated frequency, the flux is rated flux, and that is near the saturation point. We cannot increase flux anymore. It will lead to saturation in the core of the motor. So this means that you cannot reduce the frequency. Uh, Otherwise it will increase the motor flux. So what you can do here is that if you reduce the frequency to reduce the speed, you can simultaneously reduce the voltage V so that V by F is constant. So if the V by F is constant, the flux will remain constant, or more strictly speaking, E by F should remain constant. This is approximation that V is equal to E at rated voltage. This approximation may be very correct, but at lower voltages the voltage drop will be significant and E and V will not be exactly equal or nearly equal. So near rated frequency, you can say that if you maintain V by F constant, the flux will remain constant. Now let us see what happens when we reduce the frequency maintaining V by F constant. That is, we reduce the frequency and simultaneously reduce the voltage also, so that the factor V by F remains constant. So let us see what is the expression of the maximum torque. Just recall it: 3 upon 2 omega ms, synchronous speed in radians per second, V square upon Rs plus minus Rs square plus Xs plus Xr dash square. Now in this some factors depend on the frequency. So what are these factors? Omega ms, it is a factor of frequency, and the leakage reactances of stator and rotor windings, they are also frequency dependent. So let us write in terms of frequency. So this 3 upon 2, 4 pi f upon p omega ms, b square upon rs plus minus rs square plus, here it is xs is equal to omega ls, and omega is equal to 2 pi f. So you can write it as 4 pi square f square ls plus lr dash square. So now this is a constant 3 upon 2 into 4 pi upon p. Let us give it a name. So this I have given as this constant I have taken as k. So it will be simpler now. K upon f, b square upon rs plus minus rs square plus 4 pi f square ls plus lr dash square. Now here you just divide it by f square. both numerator and denominator and simplify it. You can write it as k into v upon f square, and in the denominator it will be rs upon f plus minus rs upon f square plus 2 pi ls plus lr dash square. Now here one thing you can note that the value of rs upon f is much less than this factor 2 pi ls plus lr dash near rated frequency. That is, when the frequency is close to rated frequency, then this will be negligible. So if near rated frequency, when the frequency is not very low as compared to rated frequency, then you can safely neglect this term as compared to this term. So when you neglect this term, so this will go, and you will be left with 2 pi ls plus lr dash whole square outside the bracket. This will go, and you will have only 2 pi ls plus lr dash, and as compared to this component, rs upon f is negligible, so you finally get T max is equal to k into v by f square upon 2 pi ls plus lr dash. Here plus and minus are for two modes of operation, that is motoring mode and generating mode. So this indicates that if you maintain v by f constant, the maximum torque of the motor will remain constant. And it is obvious that when v by f is constant, the flux is constant. When the flux is constant, the motor torque will remain constant. So this means that the maximum torque of the motor will remain constant if we keep v by f constant. That is, we reduce frequency, and in same proportion you reduce the voltage also, so that v by f is maintained constant. If we do that, the maximum torque will remain constant, or you can say that the torque handling capability of the motor will remain unaffected. But this is with the approximation that E is close to V, which is not always the case. At lower voltages, this approximation is not valid. So what happens is that if we maintain V by F constant throughout, then at lower frequencies, when we reach near zero speed, then the maximum torque will decrease. T max will decrease. So this factor will not be negligible, and then the effect of this change will be there, and the maximum torque will decrease. So what is the remedy now? We can keep V by F constant near rated frequency, and as the frequency reduced, say it is less than 50% or 60%, then we can slightly increase the voltage, slightly increasing the V by F, so that the constant torque is maintained. The T max remains constant at its rated value. So this you can do. You can make a calculation, and you can form a lookup table that at this frequency this is the voltage, and at this frequency this is the voltage. So in that way you can maintain certain voltage that keeps the maximum torque constant at its rated value. So I have shown here that for rated voltage and frequency, this is the characteristics of the motor. And if you want to reduce the speed, then you reduce the frequency. Suppose we have reduced the frequency by a factor 20%. So F1 is 0.8 times Fr. So you have to make V1 equal to 0.8 times Vr. That is, V by F is constant at its rated value. So we have done the reduction, and at this level the maximum torque is same as it was at the rated conditions. But if you further reduce the frequency, say you have made the frequency as 0.3 times the rated frequency, then the voltage, if you make voltage also 0.3 times the rated voltage, then the maximum torque will decrease slightly. So if you want to increase the maximum torque, then you can increase this ratio. So V2 is made only 0.4 times Vr, as I have shown here. It is not an exact calculation, just to demonstrate what we do. So you have reduced frequency by a factor 0.3, made it 0.3 times rated frequency, but the voltage is made only 0.4 times the rated voltage. So that is, V is increased slightly from what it should be done to maintain constant V by F. So if you do that, the maximum torque can be maintained constant. So you can see that if you reduce the frequency and simultaneously changing the voltage such that maximum torque is maintained, the characteristic is like this. It is shifting parallel to itself. And one more thing you can note here that the starting torque is increasing. At rated conditions, this was starting torque. At 80% of the frequency, this is the rated torque. At 31, this is the rated torque. So this means that as you reduce the frequency to reduce the speed, the starting torque will also increase. So this means that from here you can just conclude that if you want to at the time of starting, you can reduce the frequency and that will increase the starting torque. And you can show that if you reduce the frequency, the starting current will also decrease. This means that there is an excellent method of starting the induction motor. You reduce the frequency and voltage also to some extent. That will increase the starting torque, but it will decrease the starting current. So when we are having this V by F control facility, then you can start the induction motor like that. So this was the speed control below the rated frequency, rated speed. But you can control the speed even above the rated speed, rated synchronous speed. So for that, you have to increase the frequency. But the voltage cannot be exceeded beyond the rated voltage. It will affect the insulation of the motor. So voltage has to be maintained constant at its rated voltage. So this means that if you increase the frequency to say 20% higher than the rated frequency, voltage has to be kept constant at the rated value. This means that if we increase the frequency, keeping voltage constant, the flux will decrease. So once the flux decreases, and you can prove it from the equations also, the maximum torque will decrease. So the maximum torque I have shown here is like this, and the starting torque is also less. So if you further increase the frequency, say you have made it 1.4 times the rated frequency, the voltage is maintained constant at the rated value. Again, the maximum torque will further decrease. So this means that you can control the speed even above the rated speed, but at the cost of torque handling capability of the motor. The motor cannot handle the same torque at it was able to handle at the rated voltage or below the rated voltage. So speed control is possible in the whole range, but above the rated speed, the torque handling capability will be sacrificed. So this is an excellent method, and you just can control the speed over the whole range and maintaining the torque capability below the rated speed. Usually we control the speed below the rated speed only. So in this range, it is an excellent method. But if you want, you can go for the speed more than rated speed, provided the torque requirement is low. So in that way, you can control the speed in the whole range. So this is very good method and most preferred method. But here, as you see, it is complex method. You have to simultaneously change frequency as well as voltage. So that makes us the system more complex. So in the next lecture, I will explain what are the various ways you can implement this frequency control method. So that is all for today. Thank you.